Okay, so the very first thing to talk about is kind of what you do every day without thinking about it, which is that you're using the web as the world's largest deployed and working client-server system. Right? So what do we mean by that? And by the way, this is just an aside/advertisement. Read the book. Okay. It does not replace reading the material. We're just trying to give you additional perspective here. Okay, so what does the web look like? We're going to use an analogy of altitude. We're going to start at about 100,000 feet out and then zoom in progressively to more and more detail. And at the very top level, the web is a client-server architecture that's request-reply oriented. So what does that mean? It means that a web browser sends a request to a website through the magical cloud called the internet, which is present in every talk about networking. And the website replies to that request, sends something useful back to you, or possibly an error message. Okay, so that's at the very top level. That's what this is. And in terms of this picture that we're going to see over and over again, this is a picture that's taken straight out of the book. So we're kind of at this top level right here. All we're going to do is talk about what's going to happen at this level. We've got a browser like Firefox or Chrome, and we've got a site like Rotten Potatoes, which is the instructional example we developed through the book. If you've used Rotten Tomatoes, this is a very simple version of it. So what's going on at this kind of 100,000 feet level? And when we say that it's a client-server architecture, right? Whenever I use the word architecture, there should be a Pavlovian bell going off in your head, which is telling you, by choosing an architecture, you've rejected an alternative, right? By definition, an architecture is a way that you put things together, that you logically organize them. So if I'm telling you the web is a client-server architecture, you should immediately assume the implication is other architectures are possible, and the web is not those. So we'll talk a little about what the other ones are and how the web came to be not those. So the most common other architecture in network distributed systems is the peer-to-peer architecture. Roughly speaking, when we talk about the high-level architecture, and soon we're going to get to what's inside each of these boxes, in a client-server architecture, you've got typically a single logical server. It's serving a large number of clients, probably doesn't even know who they all are or how many of them there are. And the idea is, generally speaking, the client asks a question, the server provides the answer. Right? That's, generally speaking, the client-server architecture. So over time, the client and the server software get to be quite specialized for their tasks. Right? The client's job is interact with a human being, typically, and ask questions on behalf of the user. The server is supposed to wait for people to ask questions and then serve many clients at a time, efficiently answering those questions. An alternative, if you use something like BitTorrent, is the peer-to-peer architecture, where roughly speaking, any given participant can be either a client or a server. Now, I'm not saying that one of these is inherently better or worse than the other, but it is the case that in a peer-to-peer architecture, because you've got to do both jobs, you tend not to end up hyper-specialized for either one. In addition, especially now that you've heard about warehouse-scale computing, you could see why the warehouse-scale computing model vis-a-vis, y'all with browsers is a much better fit for client-server, right? We've got the economy of scale in the big server box. That's these concentrated warehouses full of trailers full of computers. And then you've got a lot of clients that are much simpler, and these are usually on people's PCs. So the client-server model is a better fit for the web, and they sort of have evolved hand in hand in that regard. So client-server is the first of many design patterns that we'll see. A design pattern can actually be applied at many different levels of abstraction, but basically they're ways to capture common structural solutions to recurring problems. Right? So the idea is you've got a thing that has a bunch of information, can answer questions. You've got a lot of people that want to ask questions. Regardless of the implementation, you could talk about that as a client-server system. Yeah, browsers versus BitTorrents. OK, so what about the nuts and bolts? It's a client-server system, but how do things actually communicate with each other? I'm going to condense like 45 years of TCP/IP history into one slide. So again, I'm giving you the high-order bits that you need to know to get through the rest of this course. If you've taken a networking class, you'll have seen some of this before. The first kind of buzzword you need to remember, IP address or Internet Protocol address. It's basically 4 1-byte numbers separated by dots, and they ideally uniquely identify one machine on the Internet. One address is special. Actually, several addresses are special, but for our purposes, this one is super special. 127.0.0.1 always means the computer that I'm typing this on, right? It's localhost is a special name that's applied to it. And even if your computer is not connected to the Internet, you can always assume the existence of this special address and the special name that goes with it, right? Localhost is always available, and you can always behave as if it were an actual computer, and you can do Internet operations against it. Communication between these entities occurs over a pair of protocols called TCP/IP. IP is the simpler of the two, and it is a no guarantee best effort service that says, I'll deliver a packet from one internet IP address to another internet IP address. Best effort means it might not work, and don't ask me if it worked later, right? Just hand it to me, and it's your job to do some other processing to figure out, maybe ask the other side if they got it. That's TCP's job, the Transmission Control Protocol. It's a layer of software that runs on top of IP, and it detects that packets maybe get dropped because things are arriving not in the order I sent them, or there's gaps in the sequence of when things are arriving. Maybe the network is slow, so things are being dropped. And it takes various actions to respond appropriately to that. And what if you have multiple different applications on the same computer and they all want to use TCP? No problem. There's an entity called a port number, which is just an integer that identifies this is the address that I'm listening on for this computer. It lets many apps on one computer all use TCP IP. Continuing in our tradition of identifying Turing Award winners who are influential in shaping software as a service, Vint Cerf and Bob Kahn, the godparents or something of the internet, they shared the Turing Award for fundamental work on the internet architecture, including the way these protocols are designed and why their responsibilities are divided the way that they are. And kind of the brilliance of the design is that from the point of view of somebody trying to use TCP IP, the illusion is you have a string that you want to send to somebody else, like get/bears, and you put it into a pipe, and magically the string comes out the other side of the pipe in the same order that you put it in. And now the other side decides it wants to respond, and it puts another string back into the pipe, and the string comes back to you. Thank you, thank you. It took half an hour to do that stupid animation. OK. So let's jump back up for a moment. I said that the web is really just request-reply. I actually lied a little bit. There's an additional piece that I didn't mention, which is the domain name system. In reality, you almost never use IP addresses directly. You use host names, like google.com. So there's actually an additional step that I didn't show, which is that the web browser will first try to look up the host name from a DNS server. And DNS is just another software as a service, right? It's actually a very sophisticated distributed implementation of one. But from the point of view of our software as a service client-server world, this is just a different kind of server than a web server. Through a series of mechanisms we won't talk about in this class, the answer comes back. And now, armed with the IP address, we can actually use TCP IP to get the thing that we want to get. Okay, so those are kind of the basic moving parts of how you get bytes from point A to point B and how you discover what the IP address of point B actually is. Okay, so now we know how to talk to an endpoint on the internet. Now that we know how to talk to it, what do we say? Well, we say something using the Hypertext Transfer Protocol. Just like TCP relies on IP, HTTP relies on TCP. So it assumes that it can reliably send strings back and forth. And the strings are actually very simple. They're just ASCII strings that typically begin with a verb like get or post. They're followed by a URI, also called a URL. Don't worry about it. It's a URI. They'll often include the HTTP protocol version that's understood by the client. And then there's some extra information regarding the thing that I'm asking about. So the client sends over this string. And then the server, if all goes well, will listen to that string. Aha, a client is contacting me using HTTP. It's asking a question. I will respond with a confirmation that I understand the protocol version, a status code saying whether I can successfully reply or not, and then assuming I can successfully reply, some headers and the body, the actual thing that the client asked for. So let's do a really simple example of this. And we're going to get the... Let's make sure. Is that legible? Bigger? That's pretty good, right? OK. I'm going to use the famous program Netcat to listen on TCP port 8000. Remember I said port numbers let different apps on the same computer all use TCP. I'm going to hop over here to Firefox. And I'm going to type in. OK, so remember, localhost is this very machine, right? The same machine on which that terminal window is open. I'm going to specify port 8000, and I'm going to get la-di-da. OK, nothing's happening. Something's happening. OK, so what's happening over here? This is what me pretending to be a web server just received from Firefox. There's a get. Here's the thing that I asked for, la-di-da. Here's the protocol version number of HTTP. A bunch of headers that you shouldn't worry too much about, and a cookie that we'll talk about shortly. Now, let's just cheat and reply hello world. The standard reply to all computer science questions the first time you see them. And then we will close the connection. Ta-da! I don't know if you can read that, but it says hello world. OK, hardly magic, but that HTTP is really that simple. I just pretended to be a web server, and I just typed a simple string back to the client. We can do something a little bit more realistic. What if we do this to a real web server? Where is my... There we go. OK, let's go to a real web server. Here's an ancient utility that predates all of you, and possibly your parents. I don't know. But we're going to go to the Berkeley website. Port 80, right? Remember port numbers? Port 80 is the official and blessed port for HTTP, because the Internet Assigned Numbers Authority says it is. And we will manually request, this is what your browser would generate if you actually type the URL. And I'm going to say, I'm a really ancient HTTP client. OK, bunch of garbage which you don't have to worry about. We're going to learn more HTML in a minute. But again, what's the message? HTTP is a brain-dead simple protocol. I open a TCP connection, I send a one-line command, and I get a bunch of stuff back. And if we scroll up just a little bit, more than a little bit, this much, here's what I got back from the server. Right? Here's this first line, protocol version 1.1, we're good with that. 200 is one of the family of codes that means all is well, OK. Everything after the 200 is for human readable eyes only. A bunch of headers that, again, don't worry too much, but they tell us more information about the thing that is about to be returned. A blank line, and then stuff. And the stuff is what I asked for. This is pretty much all there is to HTTP. Cookies. So HTTP is a stateless protocol. You may have heard this before, but this actually turns out to be profound for a number of reasons, which we're going to see in just a few minutes from now. Stateless just means that every HTTP request from a given browser to a given server is independent of every other request. It's like all the other ones never happened. There is no connection whatsoever between them. And you can imagine that as websites started to become popular in the mid-90s, this problem arose. I want to create a site that has a multiple-step procedure, like add something to your cart, check out, right? So that means that somehow it's got to remember where you are on the site. And if every HTTP request is independent of all the others, how are we going to remember that? Originally, people thought, well, let's see, we could use the IP address. We know which IP address it's coming from. We could use that. But it turns out if a computer is in a public space, that doesn't work so well. And also, if you're doing like home networking, if you've got a router in your home, they do a bunch of technical tricks so that all the machines in your house actually appear to be sharing a single IP address. So this trick wouldn't work too well. What about we'll put some extra stuff into every URI that will sort of be some junk that identifies each user. And we'll actually see more of this when we talk about our introduction to Rails. But very quickly, as the web became popular, it became clear that a way to serve a lot of people would be to cache or keep copies of frequently requested pages at various ISPs so that not every single request would have to go all the way to the website. The problem is that the way that you remember which page you're caching is by the URI that references that page. So if you put a bunch of extra junk into the URI to identify the user, that breaks caching, right? Now you've got a bunch of users all requesting the same page, but it looks like they're requesting different pages because of mismatches in the URI. So after a short time, cookies turned out to be the answer. And there's a very good screencast that you can watch that we carefully made showing how they work. But just briefly referring back to when we contacted the Berkeley website. When we contacted, here we go. OK, so this is an example of a previously served cookie that Firefox is sending back to the website. The idea is that the website has the option of returning a cookie when it gives you the answer to your first question, and your browser is supposed to remember that cookie and make sure that it sends it back every time it talks to that same server. So the cookie gives you a way at the server side to say, aha, I know this is the same user because I'm going to send each new request a unique cookie, and if the request doesn't arrive with a cookie attached to it, this must be a new one, which is why a lot of websites don't actually work if you don't have cookies turned on. So as soon as the mechanism was invented, people started using it for all kinds of things, right? For customization, you can set up your Yahoo or Google homepage to look different. flow tracking and click tracking, right? How long do you spend on a page before you click on something? Whether you're logged in or not, right? You do a procedure to log in, and once you are logged in, a cookie is issued that indicates in some way that you're authenticated. As long as you keep supplying that cookie, you don't have to log in for every new page view. So I'll leave as a sort of question for the reader, which of these could be implemented as client technology. But a hint in terms of thinking about this is, in software as a service, you can never trust the client. Right? The client could be a bot. The client could be a user who's using a really out-of-date browser. The client could be a script that's running awry. You have to assume that all clients are untrustworthy and evil. So serve a cookie, get the cookie back, but the cookie has to be constructed in a way that you could verify that it's actually legitimate, hasn't been tampered with. And when we talk about the Rails framework, we'll see how Rails does that for you.